Hello everyone. First of all, this is my great pleasure to have this lecture on rock fractures aiming towards mining applications for the ISRM Commission on deep mining. And I would like to express my special thanks to the ISRM Commission on deep mining and the chair, Professor Abbas Taheri of Queen's University, for this kind invitation. So my name is Giang Nguyen. I'm currently an academic at Adelaide University, and I put the logo here of our new Adelaide University, but all the work here has been done under the banner of the former foundation, University of Adelaide. So the topic today is on the fundamentals of energy principles for control rock fracture, aiming towards obtaining intrinsic rock fracture properties for predictive simulation. And of course, the applications is mining, deep mining, or any other mining related ones. And shortly about myself, I grew up in Vietnam. I got my degree in civil engineering from the Saigon University of Architecture in Ho Chi Minh City, Vietnam. It was followed by my time for a master degree in civil engineering, but the major is computational mechanics from the University of Liège, Belgium. My PhD is from the University of Oxford in the United Kingdom. The major one is my major is computational mechanics. So I spend my time, academic time, at a postdoc in the Department of Mathematics and Statistics at the University of New Mexico, Albuquerque, for about 1.5 years, followed by so far 17 years or so in Australia since or 19 years already since 2007 from the University of Sydney, and the last 13 years from 2013 up to now I've been at the University of Adelaide. And the university has now merged with the University of South Australia to become Adelaide University, starting from 2026. So my major, my expertise is computational mechanics, mainly fracture of brittle and also ductile materials, with applications in civil engineering, resources engineering, mining as an example, and also mechanical engineering. So my presentation today is mainly on the energy principle. We have three interrelated topics on energy principle, starting with the theoretical approach, followed by experimental one, the use of energy principle in stabilizing fracture processes in testing hard rocks. And the final one will be a computational approach on how to control fracture in simulating rock fracture, with particular focus on the snapback or class 2 behavior. So the main aim is to have more controllable and reliable simulations at all scales, but towards the ultimate goal of having predictive simulation for underground operations. So all scale here means lab scale mainly, and very large scale, say our simulation here using particle methods, the NPM, for the lab scale, and the smooth particle hydrodynamics for the deep mining operation, KV in this case. So we start first with the theoretical approach, where I will explain the importance of energy principles and the use of energy principle to predict rock burst in mining operation. So at first, this is the test to give us an idea about why we need such a thing, say energy principle, and how useful that is. So this is the ISRM standards or recommendation test using the chain extensometer on the universal compression of a sandstone in this case. So if we are able to successfully control the test, the result will be shown later. We can see the strength evolution and in the end shear band like this. If we plot the evolution of von Mises strength across the shear band at different stages, we can see such a kind of strong inhomogeneity well beyond the acceptable range for what is called homogeneous kind of material behavior. That happens mainly close to the peak, and beyond the peak, this strength localization intensifies, and in the end, clear shear bands occurs, separating the specimen into two parts. If we plot the evolution of strength, say axial stress and time, together with three different strengths, the strength inside the shear band, the red zone here, the strength outside the shear band, and the macro average strength, we clearly see the bifurcation point, beyond which all these three strengths are following different paths. And outside the shear band, unloading happens. As you can see, somehow the reduction of strength outside the shear band, while the von Mises strength inside the shear band keeps increasing. The macro one, average one over the surface here, is the average, volume average one. And this is telling us something. This is bifurcation, beyond which we don't have a single stress-strain relationship anymore. Stress can be very similar, but strengths, as you can see here, they become very different. The macro strength, the volume average one, and the strengths inside and outside the shear bands, they are very different. Now, if we plot, say, if we test three different aspect ratio, length by diameter, 1.5, 2.5, and 3.5, we plot the load displacement curve. We got these three curves, very distinct, and the longer the specimen, the softer behavior. Softer means the stiffness is lower, the initial elastic stiffness, and the post peaks are also very different. But if we normalize everything as we usually do to get stress and strain behavior, we can see that the elastic stiffness is almost similar. Some small variation here are mainly due to the inhomogeneities of the material across three different specimens. The post peaks are very different, so stronger softening or snapback for the longer specimen, say length to diameter of 2.5 and 3.5. So the question here is that which stress-strain relationship will we use? We know the strain will be different, so we plot the average one here. They will also be different across three specimens. And if we do a further step in using digital image correlation to work out the stress-strain relationship, stress is assumed the same roughly because they need to meet equilibrium condition across the shear band. Strain, as we know, they are very different. And if we plot the macro stress against strain, inside the shear band, the red one here, outside the shear band, and the macro, the black one, we see three distinct behavior: unloading outside the shear band, the blue one, and strain intensifying inside the shear band, the red one. The macro one is in fact the rolling average one. And in this case, we cannot use the macro one because we cannot use we cannot use the volume average one here to represent the behavior of the material. We go one step further to look at energy dissipation. I represent here the load displacement curves of these three specimens, and under idealized condition, assuming the two specimens length to diameter ratio of 2.5 and 3.5, roughly they have almost or very close shear band angle, and ideally under the same stress conditions and same material, this shear band angle should be the same. And it is the case when the length to diameter ratio is large enough. So we consider these two cases here as an example. So the conclusion here, say if they are under the same stress conditions, they should experience or they should have the same shear band angle and the same dissipation. That means dissipation due to the creation of the shear band and evolution of the shear band. So if the dissipation here is due to fracture, it is scaling with the surface area due to the creation of new surface areas. But if we look at the whole specimen, they're under the same stress condition. We look at the peak, they store different amount of energy. So the peak here of all the three specimens are roughly the same, and theoretically they should be the same because they are of the same material, and use or failure happens at peak under the same stress threshold. The area under this curve represent the energy stored in the specimen, and the stored energy here scales with the volume. So the larger specimen, the larger amounts of strain energy at peak is stored in the specimen. So if we look at these two cases as example, we plot the load against displacement. We can see that at peak, this specimen is storing some amount of energy, sigma, that is scaled with the volume of the element. A is the cross-section area times the length, and the 1/2e sigma c squared, with sigma c being the compressive strength, is the strain energy, that is energy per unit volume. The dissipation in this case is scaling with the area. So given the shear band angle and the cross-section area, we can work out the area of the fracture or shear band. Assuming the dissipation per unit area is GF, we have the dissipation of the specimen at the end of the failure process. So snapback or class 2 behavior here happens if the storage is larger than the capacity of the specimen to consume energy. So that is the case. As you can see here, the red area, snapback happens if the red area is smaller than the hatched blue area. So that means for the same materials, same properties, the longer the specimen, assuming they have the same cross-section area, the more brittle load and displacement is, and hence the stronger snapback, more snapback is observed. This is what we have seen earlier in the previous slides. And to control it, we need to remove the excess strain energy in the specimen so that the test or the test machine can successfully capture this kind of snapback. If not, very brittle or violent dynamic behavior will happen, as you can see here from our test on direct control, vertical displacement control. So what can we do here? If we know this energy principle, we bring it or we proceed with a further step in using this energy principle in predicting rock bursts. As you can see here, a video of rock bursts in underground operation. And we consider the stress condition and a certain type of specimen with this kind of prismatic shape. We know that from our theoretical work, failure happens. Failure depends on the stress state, and the shear band or localization orientation depends on the stress states, as you can see here. This is the result, illustrative result from our papers, validated with experimental data. And we use this kind of failure pattern and corresponding dissipation, because dissipation mainly happens on the shear band or on the fracture surface. So we use that to bring it to mining operation to predict rock burst. So if we consider this kind of prismatic volume element with W and depth B, length is L, H is given under three principal stresses, sigma 1, sigma 2, sigma 3. We can work out the elastic strain energy stored in this volume element before the release of stress in one direction. And as you can see here, it is scaling with the volume of the element, and 1 by 2 C ij KL, sigma ij, sigma KL. It is the elastic strain energy stored in the volume per unit element, per unit volume before the failure. So if one principal stress is released, failure is assumed to happen on that plant, and the dissipation capacity of the specimen scales with the surface area of that plant, and we can work out the dissipation capacity in this form. So rock burst in this case happens if the specimen stores energy more than the capacity to consume it. That's the ratio, and that's allow us to give an indication or even magnitudes of rock burst. So if storage is greater than capacity, rock burst can happen, but this is not always the case, because it still depends on another sufficient condition, which is the failure criteria. And this is a simplified presentation of a more slightly technically complex one. Some details are neglected here just to make the presentation easier to follow. You can have a look at our paper here, published a few years back. So now this is the illustration, how things work, how we use the concept of burst envelope here to help predict rock burst. We have the first stress path, say that is the stress path going out of the burst envelope. That means the energy stored in the specimen under this stress condition is potentially leading to bursting if because the storage capacity is greater than the dissipation capacity of a single shear band in this case. And if we unload it, meaning we release the stress, one principal stress, it is shooting outside the yield surface or failure surface, the red curve here. Then it will indicate bursting because in this case two conditions are met. The stress point, initial one is outside the burst surface, and the one after stress release is also outside the failure surface, so bursting will happen in this case. But the second stress pass, this is giving us an indication of burst potential, but when one principal stress is released, the stress path is shooting, is pointing, going back to inside the yield surface or failure surface. So in this case, these two conditions are not met, so no failure or no bursting as well. The third case, both points, beginning and after the release of stress, principal stress is inside both the burst envelope and the failure envelope, so no failure happens. The other scenario is the case of stress point at the beginning and the three principal stresses inside the burst envelope, but when one principal stress is released, it is moving outside the failure surface. In this case, no bursting happens. So we have this theoretical illustration and also the validation here. Only one case with this stress part 1, which leads to bursting, is used here. So if we load the prismatic volume element to a certain stress level, sigma 1, 2, 3, follow this kind of stress paths, and we release stress in one, we release one principal stress. In this case, the stress point is, the final stress point is outside the failure envelope, and bursting in this case theoretically can happen. So our discrete element simulation also following the same kind of stress condition, and the release of one principal stress in this case leads to violent dynamic behavior, which is an indication of bursting. So this is the case of bursting, theoretically predicted and verified using numerical simulation. Of course, this is a simple enough illustration of the concept followed by verification. It will take a lot of work and time also to bring this to practice, how to apply this one in deep mining situation. So we are still working on that. So I have shown the theoretical approach on why energy principle. We will apply some of the things that has been presented in the previous slides, in the previous part, on stabilizing fracture processes in rock testing. So the main aim is to get more intrinsic properties. Say an example here is the fracture energy in loose sense at the mesoscale of the fracture. Mesoscale here, the scale of shear band or fracture surface. And we'll show some test results and implication as well. So at first, it's about snapbacks or class 2 behavior. We use an example here, a 1D example, because it's always easier, more straightforward to use 1D example. So we indicate 2 points here, P1 and P2, along this stress path. And correspondingly, we have 2 displacement, delta 1, delta 2, on the snapback kind of positive curve. So under tension, we use tension here. we know that the zone outside the fracture process zone, the red one, is shrinking, and the fracture process zone here is extending. So that means fracture always happens in a very localized, small, localized area with small width. The width of the fracture process zone is small. So if this is the macro load displacement behavior, they are the combination of two behavior inside and outside the fracture process zone. The red zone here is expanding, while the blue zone is shrinking, indicated by the two different parts here. And they are under the same stress condition or under the same load here if the cross-section area in the red and the blue zones are the same, which is the case assumed here. So the macro one is the volume average one of the red and blue one. So snapback happens when the blue one is shrinking more than the expansion of the red one. And this is the one we may have in experiments. So say if we have a longer specimen, the blue zone is getting bigger, while the red zone is almost the same, because if they're of the same material under the same stress condition, then the fracture process zone is the same in these two specimens, longer and shorter one. So in terms of energy, that means this one. The gray area here is the energy stored in the specimen at peak, but the snapback here, the red area, is the energy the specimen can consume. If we give the specimen more energy than its capacity to consume through a single fracture process zone or shear band, then more shear band or even very violent behavior must happen to consume such amount of excess strain energy, the difference between the red and the gray area. So we use this principle in testing to control the fracture process, and the principle is based on the control is based on PID, which stands for proportional, integral, and derivative. So say if we have these two things and we are using the expansion of the red zone to control the process, it means the crack opening in this case should be having follow the rate of crack opening should be following the specified value that is used to control the fracture process. And if this is expanding more than the specified one, unloading, slightly unloading will happen. So this kind of loading, unloading process under using PID control will gradually remove the excess strain energy and allow us to capture the whole fracture process in a very stable way. So we use this in this case to a few different kind of tests, and one of the more challenging one is the Brazilian disc, and in this case we use lateral expansion here from an LVDT to feedback to the control, so that the loading process, the vertical velocity here, can be adjusted gradually to gradually remove the excess strain energy. Of course, this is just one example. Other example includes the use of acoustics energy release or dissipation, if we have a way to measure it, as the control. The dissipation or energy release happens mainly inside the fracture process zone at the mesoscale. the quantity that is related to mesoscale here can be a good one for the control. It could be acoustic energy release, dissipation, or expansion of the fracture processor. The same principle applies to triaxial tests. In this case, we use lateral strain attached to the membranes here for testing hard rock, and we can manage to capture snapback even under sufficiently high confining pressure, say 60 MPa here for a hard rock. This kind of control, we call it auspice, Adelaide University Snapback Indirect Tensile Test, or Advanced Universal Snapback Indirect Tensile Test, has been applied to a range of materials from soft rock, sandstone, to hard rock, a kind of granite, bluestone, and even concrete. Concrete in this case is exhibiting class 1 or normal softening behavior. And the technique here was able to capture both class 1 and class 2 behavior for a range of materials, as you can see. So what happens here at small time scale? We already mentioned, or we have addressed the release of strain energy to stabilize the fracture process. So we use this example of a successful Brazilian test using auspice, our control methods, to show the principle and how it works. So if we look at a short time windows, 30 seconds in the post-peak regime, which is this one, we can see the effects of loading and unloading here if we plot the load and vertical displacement together. So the curve that looks smooth here at the glance, when we zoom in, has this kind of behavior. And this is the consequence. If we look at, we plot the load, vertical displacement, blue one, and lateral displacement against time. And we have 30 seconds time window here. You can see that the vertical displacement is following the downward trend, that is reducing, indicating snapback behavior or class 2 behavior. The lateral displacement, which is used, this one, to control the whole failure process, is going up and down like this, but the overall trend is that it is always increasing, meaning fracture or failures is gradually happening. And the unloading and reloading process in a very small time scale, as you can see here, will allow the gradual release of excess strain energy, so that this kind of snapback can be successfully captured. So we use this kind of test to work out two things reliably: the tensile strength. We know that Brazilian disc testing will give us some indirect tensile strength close enough to the direct one, and we go a step. We move further in this direction, inducing this successful snapback test using auspice to work out or to obtain mode 1 fracture energy as well. So if this is successful from a single test, we can get two important properties: tensile strength and mode 1 fracture energy. So this is different from standard test on using 3-point bending configuration. The load in 3-point bending test dropped to 0 at the end of the fracture process. So for Brazilian disc test, if the displacement is fully split, the two halves of the displacement can still hold a significant amount of load. And the point here is to identify the moment of fully fractured. The displacement is fully fractured. And once we have identified that, assuming this is the one, the moment at which the two specimen splits into two halves. The two halves can still store such amount of strain energy, assuming this is the unloading slope at this moment. The energy dissipated due to fracture is the blue one here. This is the area limited by this kind of curve. And the specimen, the surface, fracture surface, in this case, is just something in the middle of the specimen that can be worked out. We can work out the mode 1 fracture energy by this one. Energy dissipated divided by the fracture surface S calculated, or can be at least can be worked out from the broken specimen diameter and thickness of the specimen. So if that is successful, we can work out two important properties: indirect tensile strength and mode 1 fracture energy. So the remaining point, how to determine this point, the moment of complete splitting. So we use a few things here to identify or pinpoint when it is fully fractured. So first, at the moment of fully fracture, we observe in all tests so far a jump in both vertical and lateral displacement. So if we plot them together as the moment of complete fracture, the lateral one is exhibiting this kind of jump, the orange one. The vertical displacement also exhibiting something very similar. And this kind of behavior is also confirmed using acoustic emission. At this same moment, or at least roughly the same, they all exhibit a surge or a jump in the behavior if we plot the AE energy in this case. So once we have identified this, we can work out, identify the moment of complete splitting. We can work out this given point B on the post-stick curve. And from this configuration, as presented earlier, we can work out the fracture energy of the specimen, of the material. So this works, and if we make a comparison, say if we use an uncontrollable one, say like the standard Brazilian test, we usually get this kind of energy dissipation, because at the moment of at the peak, the specimen suddenly split into two halves in a very subtle way, and the energy released in this case includes kinetic energy, which we want to release. So if we do the well-controlled one using Auschwitz, we end up having close to quasi-static condition, and we can pinpoint or identify the moment of complete fracture and work out the dissipated energy and of course the fracture energy of the material. As you can see here, if kinetic energy or dynamic effects is removed, we can work out something that is the area here, the red area. This is only 60% roughly of the hash area. That means the hash area is the area we got under uncontrollable configuration. So we perform a few things here to validate our work, to validate the determination of both tensile strength, indirect tensile strength, and fracture energy. So this results presented here is the result from conventional Brazilian test. It is very fast, 12 minutes, and we got tensile strength, indirect tensile strength, and fracture energy in this case. And in this case, because of the sudden fracture and violent or dynamics behavior, the obtained fracture energy in this case is not intrinsic. It includes the dynamics effects. So if we use our well-controlled test, the fracture process is very long. It is very gradual, and we can capture the full snapback curve from which we can obtain reliably the tensile strength. In this case, slightly below the indirect tensile strength obtained from standard Brazilian disk. The fracture energy in this case is much lower than the case in which dynamics effects are not removed, which is the case of standard Brazilian disk testing. And we can have a brief idea of the tensile strength here on Gosford sandstone with the sandstone used in this test. So a long time ago we got this paper, and the indirect tensile strength in this case is 3.59, which is close enough to what we got here. The difference could be the inhomogeneity of the material, and this is still needing a bit more investigation. Coming back to what we want to have tensile strength and fracture energy. So tensile strength looks alright. Fracture energy, we need to validate it with other more acceptable methods. In this case, a 3-point bending test is used, using on 2 different types of specimen of different diameters, 84 and 106 millimeter. So this is a stable fracture process, and in the end, the load drops to almost 0. The area under the curves here in 2 cases are used to work out the fracture energy, and in this case, we have very close result. This 3-point bending test is giving us that much fracture energy, and our technique here is giving us that much, and they are very close to each other. So which indicates the reliability of the proposed test using lateral displacement control on Brazilian disk. The last part is, what do we do? We might have good enough or reliable intrinsic material behaviors, say tensile strength and fracture energy, mode 1. We can use this for our simulation, and to capture the focus here is the snapback, to capture the things we observe in experiment. So snapback here can be captured under quasi-static simulation. We'll talk about that soon. And the one we are dealing with here is the dynamic simulation. For dynamic simulation, we need to remove the excess strain energy in a good way so that the simulation will be stable. And this is the key focus of this part. So in the end, the ultimate goal is to have something reliable and controllable, because we don't want to stop at all these simulation using different methods, say material bond methods, fine elements, and particle hydrodynamics. The main aim is to go to underground operations and perform something or predict something, and our prediction must be reliable. So this is the main aim. Of course, this is a long way towards such a reliable and controllable simulation in underground operation. The main focus of this work is mainly on a few things that help us achieve this ultimate goal in the end. So first thing is this snapback. This is something well known in the community of concrete fracture. So I use here some example that we did long time back. This is 1D tension of a bar, and you can see that if we plot the load again displacement here can be obtained using different gauge length. So this is shorter, longer gauge length, and the longer the gauge length, that means the longer the specimen, the stronger the snapback we can see. And snapback in this case can be captured quite straightforwardly using it to have capture snapback under quasi-static condition. That means our governing equation in this case doesn't include the dynamics effect. It doesn't have acceleration. We remove the acceleration totally from the governing equation and solve the quasi-statics equation, and that will require the arc-length control to capture snapback. The structural problem that you can see here, using arc-length control, we can capture quite well snapback behavior for this kind of structural problem. But removing totally dynamic effects is an extreme scenario, because dynamics can happen at the scale of the fracture process zone, and we cannot always be sure that the whole structures is undergoing or experiencing quasi-static condition. So the challenge, as you can see here, is to capture this kind of or to control this kind of violent fracture process in experiments, and how we mimic that in simulation. If not, it will happen like this, very dynamics, very violent kind of behavior. And typical behavior without control is the vertical drop of load when the load gets to the peak. This is because, as explained earlier, the excess storage energy here that leads to secondary cracking and dynamics behavior, ejection of fragments to consume the excess strain energy stored in the specimen. We had some successful simulation here using discrete element method, 3D in this case, but this is still a work in progress. And we apply the same principle, the gradual removal of strain energy here to capture the snapback process and stabilize the fracture process. In this case, Brazilian disc. We show here more numerical results on 3-bond bending test on a circular semicircular disc specimen, and this is the test results, and we use what we have explained earlier, PID control, to control the crack opening. So crack opening here, this is test data, is always the rate of crack opening is constant in this case, and as a result, crack opening is a straight line like this. That's it, the test, the results obtained from our test. So in order to do that, we have the feedback here from the clip gauge, and this is giving us the crack opening that is used to feedback to the control here, so that loading unloading processes can gradually take place, and that process, that kind of loading unloading cycles, will have remove the excess strain energy from the system. So as a result, if we change the span smaller to larger, we capture a range of behavior from very strong snapback to milder and very little snapback here if the span is large enough. The question here is whether this kind of snapback can be captured using in our numerical dynamic simulation. Dynamic here means we don't remove the acceleration in the governing equation, and this is even more challenging than capturing this using under quasi-static condition. So we apply the same principle using crack opening displacement to control the simulation. The details will come in one of our paper to be submitted soon. So results are quite promising. We use the red one here, the well-controlled test, using crack mouth opening displacement as the control parameter, and when we compare it with the normal way of control using vertical displacement, we can see a clear difference. The blue curve here doesn't show any snapback. Of course, it cannot, because the vertical displacement is reversing beyond the peak. Yes, and the failure patterns looks very different. Very clean crack here in the well-controlled one, while in the uncontrollable one, fracture happens very fast. And the difference here between the two simulations is this kind of area, which is the energy used to create more secondary cracking here in the uncontrolled one. We also observe the difference in the peak load. The same parameters are used, but different type of control leading to different peak load. And the explanation here is the rate inside the fracture processor. For the uncontrollable one, beyond a certain moment, the crack mouth opening displacement is jumping very sharply. And this is indicating very high dynamics effect due to fracture and release of energy. The controllable one is very mild. As you can see here, the crack opening displacement is following what we expect. And when we compare with the test data, of course, we will not be able yet to match the test data in terms of the rate, because the rate used in test data is in experiments is very low. This is 10 to the power minus 5 meter per second. In the simulation, the red one here, well-controlled one, now is about 10 to the power minus 2 meter per second. And at the moment of the crack initiation, you can see the jump in the load in the uncontrollable test is associated with the jump in the opening here. While in the more controllable one, the controllable one using crack mouth opening displacement control, the very stable opening rate here is leading to lower peak load. So this kind of control is used in our simulation across three different spans, as you can see here, 66 to 100, and as you can see here, we can capture quite well snapback or class 2 behavior. We can use a different type of specimen to explore the effects of dynamics on the behavior. Say, under this fixed configuration, we change the crack mouth opening displacement rate, which is used to control the test. We can still capture briefly, at least to some extent, the behavior under different CFOD rate. So to sum up, this is our conclusion. We have presented three different parts. The theoretical part, stressing on the importance of energy principle. The experimental part on the application of this kind of principle in stabilizing the fracture process for Brazilian disc testing to obtain reliable and intrinsic properties, tensile strength and fracture energy. We use these kind of properties, the same principle in same energy principle in testing, in simulating rock fracture to capture snapback. And our main message here is the correlation between these three parts to get a more controllable and to obtain or to control all these processes, fracture processes. In this case, all the examples are at lab scale, but as I said earlier, the main aim is to go to the larger scale deep mining operation to have a more controllable and reliable simulation. So the correlation between these three paths hopefully will help us achieve the final goal. But of course, this is a long way. And finally, I would like to thank our collaborator, Professor Murad Karakus here, Professor Ha Bui, and our PhD student and postdoc at University of Adelaide, currently Adelaide University, and our funder, PhD, OZ Minerals, and Australian Research Council. Thank you very much.